Hello, can you hear? Lots of checkered shirts. 1, 2, 3, 4, 5, 6, good, 7. Sometimes it happens like this. Yeah. What's going on? Yeah, what happened in the tutorial? Who is still having trouble finding entropy? So first I think there's a set of problems where one example you did, right? Where there is change in U, change in state. There is also work done. You can directly go to the table and find state 1, state 2. That is from the table. What if you're not able to find S values, entropy values from the table? But temperatures are given, change in temperatures or change in pressure, those kind of change in volume, change in pressure, change in temperatures are given, and you cannot go to the tables directly and find it. What are you going to do? Huh? Okay, let's assume it's ideal gas. Let's assume it's not ideal gas either. And let's assume that there is a change in state, that it's going from liquid to vapor. How you will find Q? What if Q is not available? Very good. You have to find, what is he talking about? What is that property called? Huh? No, first law I know. What is that property called? What you just told, what is that? If I ask for 1 mark questions like this, what do you do? What is this property called? Whatever you just said. Yes, you have to say enthalpy. You've done an entire course now. Yeah? Don't say first law. It's enthalpy. So you can find enthalpy. So before that, I think you should write on some basic equation. So change in entropy of universe. So when we say universe, it contains both the isolated system as well as the surroundings that surrounding the system. So for a reversible process, there is no entropy generation either in the system or in the surroundings. There is no entropy that is being generated. There is only heat transfer that is happening from the surroundings, like he said. He quickly said, right, heat transfer, I will go and find Q. So where will Q come from? Come from the surroundings, correct? Can you write like how we just explained? Why he said Q? Because where will Q come from to the material? Write it. From the surroundings. So what is this? This is an exchange of heat transfer between surroundings and system, or from system to surroundings. That's the first law. Can you write in your own words? So whatever the surroundings gives, the system takes. And that energy will give rise to some internal energy in the material, and if it does work, it does work. If it does not do work, it does not do work. So that is the first law, where you have conservation of energy and conversion of energy. But then the second law also will say how that energy is dispersed in the system. So that if the energy is dispersed where entropy does not change, or if entropy increases, then the process will happen spontaneously. If those two things don't happen with dispersal happening, then process is not spontaneous. You have to force it. It's for you to write, guys. So again, I'm harping. First law is a simple conservation of energy and conversion of energy. Second law is dispersion of energy. If I ask fill in the blanks, what you will do? The essence of first law, dash and dash of energy. Conservation and conversion of energy. Second law essence is dash of energy, dispersion of energy. Clear? And then you write a simple commutative equation. The total change in entropy of the universe is both system and surroundings. So first law will only tell the magnitudes of the energy that is being exchanged between the system and the surroundings. Yes, the magnitudes. And then there is an exchange between them. The second law, entropy, this thing will tell you how the energy is dispersed. This thing tells you how the energy is exchanged and conserved. Clear? The surroundings is the first law. System is the second law. Right there. Clear? So you have to consider both, because there will be work also. So you have to consider both what is happening to the surroundings as well as the system. So why do we put a negative sign? Finally, when we do free energy, Gibbs free energy, because you want to write everything in terms of system. Got it? So if I remove surroundings here, what should I write? Here, if I write Q surroundings, and if I write U minus W, am I right? Correct? Yes. U equals Q plus W. Why are you guys blinking? Q equals U minus W. Yes? This is of the surroundings, correct? But if I have to write it in terms of system, what should I do? I have to put a negative sign. So when I put a negative sign, if I write everything in terms of system, what do I write? For system, what do I write? No, system is positive. So I will write T ds, correct? Heat. In both cases it's heat, correct? System is TdS, yes? Here I have to write minus U minus W. Did I write correctly or no? Did I write correctly or no? Yeah, I'm expressing everything in terms of Q. I'm expressing everything in terms of Q. Did I write correctly? Yes? Did I write everything correctly? So what is this property of U and W? You just said something, right? What is the property that combines both U and W? Enthalpy. So this becomes the entropy of the system and this becomes enthalpy of the system. Then what did you get as free energy that's available for the system? You got entropy. So if you do sign change, you will get delta H minus T delta S. Everybody knows G equals H minus Ts. Yes? You get it from here only. Clear? G equals, it's not there in your syllabus, but just so that you know why universe equation is important. That's how Gibbs came up with this Gibbs free energy equation. G equals H minus Ts. Everything is entropy. Everything is entropy. That's why I wrote this equation right at the top. Everything is entropy. Got it? You can do all the work that you want, you can do everything, but the process has to be measured only in terms of entropy. Otherwise, the process will not happen. Clear? Otherwise, the process will not happen. If dispersion is not there and entropy does not get conserved or entropy does not increase, the process will not happen. The universe entropy has to be 0 or the universe entropy has to increase for every process. Otherwise, you will not have a process. That is why this equation is the equation. Don't suddenly write delta S universe is less than 0 for any process. Okay? The overall entropy can never change, or sorry, can never decrease. Clear? So this equation is funny. It not only tells you what a process is and why a process will happen, how a process can happen, it also tells you the first law and the second law, right here. The first law is right there, second law is right here. Now will generation happen in addition to the thermal entropy? Due to heat transfer, will there be additional entropy generation? Possible. It can happen both in the surroundings as well as system, and that will only lead to further increase in entropy, which is feasible and possible. Clear? You not only can have same entropy or increase in entropy due to heat transfer, that is called the thermal entropy, but you can also generate entropy due to, let's say, a chemical reaction. Let's say due to mixing in your material. That you have not taken into consideration as thermal entropy. Got it? Thermal entropy does not consider mixing. Mixing is configurational entropy. That will become combinatorial entropy. So the overall entropy will combine all these things. Thermal entropy, mixing entropy, chemical reaction entropy. So if that gets generated, so be it. It got generated. But it will only go in the direction of increase. There is no decrease. Clear? That is why you have to consider both system and surroundings, because you will come up with a reaction and say, I'm making a reaction where the viscosity increased and things got bound. Correct? In the material, but you have to take the surroundings also into consideration. Then you have to calculate the total change in entropy. Yes? That is why this is important. So don't simply focus on the system. If the system also decreases entropy, that's fine. Then you should know what has happened to the surroundings. So it will be an exothermic reaction. The heat will go out and the entropy in the surroundings will increase. Clear? Yes? Pay attention to both SYS and SURS, system and surroundings. You didn't tell me the correct sign, you should put U plus W. Isn't that right? U equals what? Q minus W. Q equals what? U plus W. Yes. Wake up everybody. Why you make me write wrong sign here? U plus W. U plus PdV is H. H. That's how you got enthalpy. Got it? You just derived your Gibbs free energy equation here. I converted everything surroundings to systems. That's why I put a minus sign. In this delta S, you can still write H of surroundings, but I don't want to write H of surroundings in the final equation. I want everything to be written in terms of system. So I put a negative sign. Got it? Whatever the surroundings gives up, the system takes. Whatever the system gives, the surrounding takes. Clear? That's why I put a negative sign. Here there is a plus sign. Why it suddenly became minus? I converted the entire surroundings to system. Clear? So that's how you got G equals H minus Ts. So then if a process is possible in a system, the free energy should always, how can it decrease? Two ways. H should completely go down or S should increase a lot. Only then G will go down. Clear? G equals H minus Ts. Write it. How does G go down? H has to go down or S has to increase. That's how a process happens. So I converted all the surroundings to system. Yeah. Yeah, it's just sign change. You can change it. That's like final to initial kind of thing. You can change. But it's not for deriving Gibbs free energy that I'm doing this. This is for you to understand that this equation actually controls your entire process. Got it? This first equation. And that your first law and second law both are there. So this is your entire red book right there. So actually you could have started your whole course by this equation. You didn't have to come to chapter 8 for this. That's all I'm saying. I hope you understand that way. And go and tell yourself, yeah, I could have done this to begin with. Yeah, you could have. And then you could have done everything reverse. Clear? This is basic common sense equation. This is real life. This is not empirical. This is coming from evidence of your day-to-day life. Which one? That one. So next time if you teach a course, you start from that equation. I'm telling you, isn't it simpler? Think about it a little bit. That equation has got everything hidden. It's got your work, it's got your P change, it's got your V change, it's got your internal energy, it's got your temperature change, it's got your pressure change, it's got your entropy change, it's got your entire chapter change. Sorry, your entire course. No? Yes? No? Yeah, you could have started with it. But people don't start like this, because if you do like this, then you won't appreciate how the thought process came about. Got it? First, people understood conservation of energy. Then people understood conversion of energy. Then Carnot scratched his head and went, uh-oh, there is something else that's happening, that there is work that is getting wasted. Then he focused his attention on the waste. Got it? Then he learned something very fundamental, that there is dispersion going on. So there's a reason for the sequence of how you go, right from you first understand work, then you understand heat, then you understand conversion, then you understand conservation, then you come down to waste. And that's how Carnot figured out. And that's how you came to entropy. But then if you put everything back, it encompasses everything. Clear? Good. So don't start like this. Students will not appreciate the history of what has happened if you simply do this. If you do this, it's over. In a month you can finish the course. Nothing. So why did I do this? No reason. Just so that you understand first law and second law. One more reason why I did this. If there is a reversible process, what will happen to the universe? Deltas of universe is 0. If it's irreversible process, it will increase. So the reason I did this is, see, he said enthalpy is here, correct? Now, if I just give you enthalpy, can you find entropy for a reversible process? Yes. So what will the enthalpy and entropy equation be for a reversible process? Delta S is 0, universe. So I will say that a process where liquid is changing to vapor, I'll give you the value of HFG at temperature T. Can you find SFG? How? Write the equation. That's why I did this. I've given you enthalpy for the phase transition, and I told you which temperature it's happening, isothermal temperature. Write it. Can you find SFG for a reversible process? That's it. SFG equals HFG by T. Got it? Clear? So all of you have done delta G equals 0 is an equilibrium process, reversible process. Delta G is less than 0, it is a spontaneous process. Delta G is greater than 0, it is a non-spontaneous process. Little bit you have done this somewhere, right? 11th, 12th, or so. Same thing I'm doing. Got it? If it's an equilibrium reversible process, delta G is 0. Then you know S is equal to H by T. That is one way. So if you don't have tables, you can ask for enthalpy values. First you should ask like what he asked. You should ask for heat. If they say I will not give you heat, I will give you enthalpy, then you should take the enthalpy values. Then you should ask, is this a reversible process? Third way, what you will do. Now you tell me, what else will you ask? Now I will not give you Q, I will not give you H, I still want you to find delta S. What will you ask me? You ask me, I will give you. What property you want, I'll give you. Huh? Specific volume temperature. No, I will not give you any of that. That's why I said I won't give you H. That was the whole point. I will not give you U, I will not give you W, I will not give you Q, I will not give you H, obviously. If I don't give you U and W, I won't give you H. Somebody mumbled correctly. Louder. No, why are you guessing? Because there's nothing else left, so you're saying, so instead of saying density and viscosity, you're saying Cp. Okay, you're taking a shot here. No, you ask properly, be decisive. I will not give you U, I'll not give you W, I'll not give you Q, I'll not give you H. I would have given you only T1 and T2. I want you to find entropy change for some blah blah process. What property do you want? I will give you whatever you want. But I'll give only if you ask. And that itself is a 2-mark question. Louder. No, there are 2 types of specific heat. No, which one? You only want Cp? What if I say there's no work done? Then you quickly say, give me Cv. I'm just doing the exam right here. Don't you get it? Yeah, your syllabus is getting revised here. If I say no work done, you should immediately shift from Cp and say, give me Cv. Okay, so you want something, Cp and Cv. Okay, I'll give you both. What you will do? I'll give you both. What you will do? So let's now take a process where there is work being done, but I don't give you U and W, but I give you want Cp or Cv? Okay, take it, I gave you Cp. Write it, everybody write it. I've given T1, T2, I've given Cp. How you will calculate delta S? You have to write an equation and then derive it. Simply no blah blah writing here. That's why I've written this equation here. Get it? It's a reversible process. So what happened to ds? ds is equal to dh by t. Correct? dh is what? Cp dt. Cp ln t. Got it? Yes? Cp ln t. Everybody clear? Same thing if I say work is not done. ds is equal to Cv ln t. Cv. Because ds is equal to only du. Just clarify everything right now. This is like doing a problem itself. Got it? So now I don't need to give you anything independently, right? Q, H, none of that is required. Problem solved. But now you have trouble, because between T1 and T2, what you will do with that Cp now? Because if you assume Cp to be constant, that will contain some errors. That also will contain errors. So what are the 3 ways when you have Cp ln t? One is you assume constant Cp, which is pretty crude way of doing. Another is you ask for a relationship between Cp and t. Plug everything into the integral, do your integration. Might become little more accurate. What is the third way? Chapter 5. You do the complete integral and find from tables with respect to a reference temperature, like S0T2 minus S0T1. That will be like the zero pressure entropy with respect to some reference temperature, the complete integral. T0 to T2 minus T0 to T1 will give you T2 minus T1. Can you write all these 3 ways? So one way is, write it man. One way is you figured how to do it if I just give you only enthalpy. You also figured how to do it if I give you only change in internal energy by using this equation. So you can write everything or list it, nicely list it. So one way is ds is equal to dh by t, correct? Yes? Correct? Another way is ds is equal to du by t, in which case work is done, in this case work is done, in this case work is not done, correct? Third, ds is equal to dh by t, but I don't know dh. So what I will do? Cp dt by t. You should put integral because there is ds, change in the entropy. Clear? Then you have Cp ln t. Keep writing. So you have ds is equal to integral Cp dt by t. Or if no work is done, ds is equal to Cv dt by t. Clear? But now you have a problem with Cp and Cv between T1 and T2. If you use constant, you will get okay, some crude value. If you put this as a function of temperature, do the complete integration, manageable. What is the third way from the table? For many gases it is there. For oxygen, nitrogen, ammonia, carbon dioxide, air. You can go to tables A.7, A.8. For two different temperatures, you have this complete integral that is done. Yes? So this integral, how do you change this integral? Okay, this value is this. This entire value is this. I put T0, reference temperature. Where do you get this integral value? Where do you get this integral value? Huh? Tables, open the book if you have the book right now. It's there in A.7 and A.8. So what is the notation for this? S0 T2. Got it? Then the same thing you write for S0 T1. You are not doing any integration. The number is already there in the book. You just have to go and take it from the book and write. Got it? You're not doing any work. You have S0 T2 and S0 T1. That's it. You got it. That would be the most accurate. But that S0 will not be given for all the materials. Got it? It's only for whatever you have in 7 and 8. A.7 and A.8. Can you read out what materials are there? Read out the materials. Louder. Nitrogen, oxygen, air, carbon dioxide, water, what else? Ammonia. Sometimes you may not get for all the temperature ranges, okay? What you will do? You put your hands up and ask, what should I do? Okay? Don't try to write a number there. If the question, whoever has set it, has not looked at the table and has gone beyond the temperature that's there in the table, then you're messed up. Yeah? That also reminds me of one more common question you always ask. There are no tables for all the compressed state materials. Of all the materials, the compressed state values are not there. So you are supposed to take saturation values. Got it? But you check in your book when you are doing the exam, and if that compressed state value is not there, you will one more time confirm and ask whoever is invigilating there, can I use saturation values? Yeah? Don't go and plug some number, whatever you feel like. I'm talking about the left side of the phase diagram, the compressed liquid state.
Table A.8 says that these values are mass based, and table A.9 says that pressure and voltage. So which one should we consider?
You should take pressure.
Nitrogen diatomic.
Yeah, take pressure. Again, careful, the entropy values is joules per degree Kelvin mole or joules per degree Kelvin grams. Yeah, careful, don't make small mistakes with all this funny things after all this. If you like to stick with grams, stick with grams. If you like molecular weight, be my guest. Put molecular weight and write everything in moles. Clear? You will get different numbers. Careful. Obviously. Clear? Now, for ideal gas, what he was saying was, if you have specific change in pressures and volumes, what you will do? Because that you cannot do from any of these equations. What you will do? You can still do it because this comprises both pressure. But what if I've given in the question, now I heat from T1 to T2 and the pressure of the gas decreases from P1 to P2. Now you find the total entropy change. What do you do? So I don't want you to use enthalpy now, got it? I want you to separate internal energy and work done. And use both and show me both and calculate your entropy change. What do you do? derive one equation. Write your first law. Write your first law. I'm not going to write it. First law. 1 mark question. State function, path function, write correctly. First law. Dou Q. What? Plus, minus. Both, plus, minus. Don't fumble over this. How much energy I have is equal to the balance sheet. I am a balance sheet. How much heat I received and how much work I did. I am like a broken record player. Yeah. So my U is equal to Q minus W. Q equals U plus W. After all this, don't make mistakes on this. Now you derive. Derive for ideal gas. Derive. Dou Q, I'll give you a hint. It's TDS. TDS. Your goal is to find entropy change. Plus PDV. Yes? Plus PDV. Now what do you want me to do? I want to find DS. Write it, don't look at it. That's why I don't write it. That's the whole point why I don't write, because you have this wonderful habit of looking at my face or this whiteboard. I'm not revising for myself. What should I do with PDV? So I will divide by T anyway. So then what happens? T is gone. So what should I write? R dV by V. R ln V. Is that correct? Very good. Now you got it. I've given you volume changes. What will you do if I given pressure changes? This is for ideal gas. You wrote PDV as RT by V. TT got cancelled here. So you got dV by V. Then you made it as R ln V. Perfect. I agree. What you will do if I given pressure changes? Write it. Let me see how you will derive. You are right. Plus, but it has to come from some other equation. And then you have to plug it into this equation. So this is your main driver equation. So this has to, that VdP has to come from another equation. I'll give you a hint. It has to come from the enthalpy equation. H equals U plus PV. DH equals DU plus PDV plus VdP. Write it. Then for DU, you put everything here. For DU. Yeah? Write it in terms of enthalpy and VdP and PDV. What did you get? TDS is equal to DH plus VdP or minus VdP? Minus VdP. You should get the equation TDS is equal to DH minus VdP. Am I right? Yes? Okay. Correct, guys? Hey, am I right or no? Plus or minus VdP? Minus. So then what is your equation? Cp. Because for DH you have Cp ln T minus V ln P. Sorry, R ln P. Yeah, you're right. Got it? Now you got the precision. So just be careful. You should know which one to use. Yeah? You should know which one to use. I actually want to get into generation of entropy. Problem is there's only 3 minutes. So in this 3 minutes, let me use to recap what I had done previously. Everybody go back to your Clausius inequality, right? Then I will do reversible and entropy generation, next chapter. Hey, can you now manage and calculate entropy changes for ideal gas when you have volume changes, when you have pressure changes, when you have U changes, when you have H changes, and when you have T changes, T. So I think these tutorial guys today you have a tutorial, huh? So they may have problems where it will keep on saying reversible adiabatic, reversible adiabatic, reversible adiabatic. Firstly, adiabatic means what? No heat transfer. What will happen to entropy? Constant. It won't change. Got it? Entropy will not change. And when they keep on saying reversible adiabatic, now what is the significance of reversible? That the universe entropy will not change, which means there is no generation of entropy either in the system or in the surroundings. So I have not gotten into explicitly, that's why I want to do reversible and irreversible process one more time, and then I will come to generation first. Yes? So generation is not there. Entropy generation is not there. So in the tutorials, if they keep asking what will you do if I give you a question with reversible adiabatic process, that means Q is 0 and delta S generation is 0. Got it? There is no entropy generation. So I think, yeah, let's spend. You wrote, what did you write for reversible process? This is a cyclic integral, correct? For irreversible process, what did you write? And I was using a heat engine as an example at that time, QH and QL. What did you write? So now you have a process here. You have A, B, and C. Going A is reversible. Going C is irreversible. Coming back, both are reversible. A, B, C. Going up and coming down. It's a cycle, correct? In one case, it will go A and come down in B. Another case, it will go up in C and come down in B. So what will you get out of this integral? No, what will you get out of this integral? That dou Q by T of A is greater than dou Q by T of C. Otherwise, you won't get less than 0, correct? So one second, let me finish this. Dou Q by T of A is less than, greater than, nah? Yeah, A is greater than. Correct, it's greater. Yeah, A is reversible. Fantastic. Just hold on. See? But as you know, change in entropy is a state function. It's not a path function. Correct? So then I can write this as dSA or dSC. So it is greater than your entropy change due to heat transfer, correct? This is heat transfer. What is this entropy change due to? Heat transfer. You have Q there. Clear? Yes? So this is a heat transfer entropy, but it is greater than that entropy. So how can it be greater than the heat transfer entropy? Because you only gave that much heat. How it can generate more entropy than what the heat has given? I just use the word how it can generate, but it can generate. That is what entropy generation is. It will give you more entropy than what you have given in terms of heat. So one component is the heat transfer entropy, which for a reversible process will pretty much be the same as how much ever heat you get, that much change in entropy you get. But in an irreversible process, there could be possibilities of where you might have friction, where you might have mixing, where you might have, what else? Irreversibilities. Insulation losses, correct? And you might generate more entropy than what the heat gives because of a physical process. Clear? Then how do I write this? ds is equal to Q by T plus entropy generation. Otherwise it won't be greater, correct? So how do I write it? Can you write it? ds is equal to, one is your thermal entropy, correct? So can you label this as correctly thermal entropy? This is thermal entropy. Can you label it? And then you can write this as ds irreversible or entropy generated, however you want to write. Entropy gen. ENT gen. For a irreversible process. For a reversible process, what happens to this part? 0. Clear? Now in your tutorial problems, you need not have adiabatic process, but they might say this is a reversible process. So you are not going to worry about generation. And generation is always going to be positive. Yes, it's always greater than 0. It's always greater than 0. Now if I have adiabatic reversible process, what happened? Quickly, this became 0, this became 0. You have a isentropic process, correct? ds is 0. ds is 0. Now if it is only a reversible process, this is 0. Got it? You should get a number. There will be change in entropy. If it is adiabatic process, would there be entropy generation? If it's only adiabatic process, possible. You can still have entropy generation in your material, in your body, yes, in your system. Got it? So then if it's only adiabatic, only this is 0. There could be generation here. There are 3 cases. Got it? One is reversible adiabatic, one is adiabatic, one is reversible. And one irreversible. 4 cases. Can you write down? In some questions, they can just say it's a reversible process. So what you will do there, generation, you will knock it off, 0. In another case, they might say it is reversible and adiabatic. Then you nullify both. Both terms, gone. In some cases, they will say that it is adiabatic. So Q is gone, but you could still have entropy generation in your body, in your system. And the last thing is, they might just say it is a irreversible process. Then you will have both. Clear? You will have both. Both thermal entropy as well as irreversible entropy. Clear? 4 cases. Irreversible, reversible adiabatic, only reversible, only adiabatic. Little bit identify this in your Carnot engine, where you have this. In the isothermal expansion, what is it? It is a reversible process. Got it? I did not say reversible adiabatic. The adiabatic expansion is reversible adiabatic. Everything is 0. It's an isentropic process. Clear? That's all I'm saying. So I don't think you have come up with a problem where it is only you might have adiabatic process, adiabatic irreversible process. You can have a question where there will be entropy generation. Yes, this term will be 0, but you will have entropy generation. Adiabatic irreversible process. Clear? How will the irreversibility come when it's an adiabatic process? Million points I'll give you. It's an adiabatic irreversible process. So you should question and ask me, if I'm not giving heat, how entropy will get generated for it to become irreversible? I don't know, you tell me. That's why you get million points. It's adiabatic irreversible process. How you will get it? Because I'm not giving you heat. Surroundings is not giving you heat, but still you will generate entropy inside. How could you generate? Huh? So what will you waste to generate this? Work. You're wasting work. You can generate entropy either by wasting heat or by wasting work. Both. Yes? So there's a fancy term for entropy generation. It's called as lost work. It's the work that you lose. That's what Carnot did. He's not getting 100% efficiency. So he went and saw what work is being lost. That's how the concept of entropy came. You're losing work. It's called lost work. Entropy generated is lost work. So for that also you can derive one equation and see how work is related to entropy generation. Next class. Catch you guys.